All right, I'm going to try and set up a little derivation that shows how pressure changes with depth into a liquid. Basically, what I want to show you is that the final result will be that pressure increases linearly as you go down through a fluid. And if there's only one formula that I want you to remember for the entire chapter, it's rho GH. So the pressure change when I go down a depth h is rho GH. And so I'm going to derive that for you right now. So the setup for the problem goes something like this. So I'm going to imagine that there is an air-liquid interface somewhere, and I'll define a top. So I'm going to draw a little symbol that's like a triangle with two lines underneath it. That symbol means air-liquid interface. I'll sort of arbitrarily define a coordinate system from the interface. I don't need to do this, but when I did this, I pointed the z direction downward and the x direction to the right. So gravity will act in the positive z direction, which is a little bit unconventional. Draw a infinitesimal element. I'll just draw like a little square with dimensions delta x by delta z in the plane that we're looking in. And I'll try and draw some pressures that are acting on the outside of that element. So I'll define the ones happening at x and z to be just p, and then if I go a distance delta z's down, that'll make it p plus dp dz times delta z. So that's just a Taylor expansion. I can do the same Taylor expansion in the x direction. So I start with p on the left-hand side, and then when I go a distance delta x, it increases to p plus dp dx times dx. Then I'll do a force balance in the x direction where gravity's not acting in that direction. So the force balance goes p times the area, which is delta y delta z, minus the pressure acting on the other side, which is p plus dp dx times delta x with the same area dy or delta y delta x. The delta y delta z's cancel, and you're left with a balance that just says that dp dx is exactly equal to 0, meaning that pressure does not change in the x direction. Pressure can, at this point, only be a function of z only. And now we'll see what that function of z is. That I forgot to draw gravity acting in this thing. So gravity acts in the positive z direction going downward on the infinitesimal element. So the force is m times g, where m is density times volume. All right, so now we do the sum of the forces in the z direction, and one of the pressures points downward, so that's downward, which is in the positive z direction, confusingly. So that's p times dx dy minus the one in the other direction, p plus d p dz times delta z times its area, delta x times delta y. We'll account for the gravitational portion, which is in the positive z direction because of the way I defined the z-axis. So that's rho times g times the volume, which is delta x, delta y, delta z. If I take a close look at that, I'll see that, I'll just circle this to show you, to make sure you keep track of the signs. Then if I take a close look, I'll see that the delta x, delta y's cancel in each term. The p terms are in both terms, and then after I do that cancellation, the delta z's are in the two remaining terms. And what I'm left with is a statement that the pressure gradient, or dp dz, must be equal to rho times g, or a constant. So if I integrate that, I'll get p equals rho g z plus an integration constant that I'm going to call p0. So again, the key result here is that the pressure goes as rho gh, meaning that h being a depth. So if I go down an additional depth h, the pressure changes by rho gh as I go down.